right, welcome everybody. Hello, my name is Ben Consolvo. I'm an AI software engineering manager at Intel. And today I'll be speaking to you about seismic data to subsurface models with OpenFWI. So it's a real world application of using PyTorch. And yeah, happy to be here today. So first I wanted to ask, why should you care about seismic imaging and FWI, or full waveform inversion? So seismic imaging and full waveform inversion, or FWI, they help us to explore for important subsurface minerals for human thriving. On the top left, I'm showing a seismic image with interpretations overlaid from the Alaska North Slope. And I worked on this during my master's degree in geophysics. And then on the bottom, I'm showing a subsurface layer with migration paths overlaid. And the second might be a little surprising for this technology, but it's medical imaging. So there was a journal article published in Nature that outlined how FWI can help find hemorrhages in the brain by using sound waves similar to how we would use it in the subsurface. So they actually use sound sources in what looks like a helmet and have receivers located around the head. You might ask, why not just use an MRI? Well, as you probably know, MRIs are expensive, not always available to everybody. And if you have metal in your body, you can't use an MRI. With this sound method of imaging, you can actually still have metal in your body and you can get imaging done safely. And FWI is a very accurate method for retrieving an image from sound wave propagation. So to find subsurface minerals to human flourishing, we need to image the subsurface with a high degree of accuracy and at a low cost. There are two main challenges I want to cover today. The first one is that the traditional physics-based FWI method that I just described, it usually requires an accurate Earth starting model in order to get to a good result. So here I'm showing kind of small images, but a poor starting model up here on the top left, and then a kind of a better starting model that would result in a much better kind of end result Earth model. But it's very difficult to obtain such a good starting model in practice. In reality, we often start with very little information about the subsurface, and it's very labor intensive to generate such a good starting model. The solution with AI is a purely data-driven approach with neural networks and doesn't require an accurate starting model. The second challenge that I wanted to address is that GPUs are typically used for fine-tuning, but are often unavailable and expensive. CPUs are often highly available, inexpensive, and they are actually now viable for fine-tuning. The new Intel Xeon CPU has something called advanced matrix extensions that accelerates matrix multiplication for AI workloads, and it's a unique feature that makes this a standout for AI for me. I wanted to show you a few pictures of my time in the field for collecting seismic data. So this was a field trip I did during my master's, actually 3 times, first as a student and then twice as a TA, where we collected seismic data and created models of the subsurface. So the bottom right 2 images show geophones, which are used to listen to the sound waves as they propagate through the subsurface. And the geophone actually has to be tightly coupled to the ground in order for it to measure vibrations properly. They're usually connected by wires run along the ground, but there are also sometimes some wireless solutions that are used. So here I wanted to show you the basics of subsurface velocity models, wave propagation, and corresponding shot gathers. Looking at the top animation, we can see we have what's a sound source propagating through the various layers of the subsurface and reflecting back up. And then the seismic shot gathers are the corresponding in time as the wave propagates across these velocity or across these Earth models, showing the wave propagation. So in this data set, the seismic shot gathers have waves propagating for 1 second and over a distance of 700 meters or around 2,300 feet. So the training data consist of a pair of a seismic shot gather image plus a subsurface model image, where we aim to predict the model from the shot gather. So I used a total of around 150,000 images of the seismic shot gathers, and 30,000 images of the subsurface models as the answer, like what we're trying to predict. And I've highlighted for you a small sample of each of the training, validation, and test sets here. So the total seismic shot images, we have 120,000 for training, 25,000 for validation, and 5,000 for test. And then in terms of the model images, I have 24,000 for training, 5,000 for validation, and 1,000 for test. I used the neural network architecture inversion net from the Deng et al. 2021 OpenFWI paper they published. It's similar to a UNet style model if you're familiar with UNet. I won't go into great detail because this is such a short talk, but if you want more detail, you can go see the OpenFWI paper for more detail. So getting into the results, I am showing inference here where I'm predicting this Earth model from the seismic shot gather. And after one epoch, we see a tiny bit of resemblance to the Earth model as compared to the ground truth model on the right. And then I ran the fine-tuning training on a 4th gen Intel CPU. And for 50 epochs, it took around 4 hours to run the fine-tuning training. And so we see a much closer resemblance to the true ground truth model after 50 epochs of training. And I never used any starting model in terms of the Earth model. I never used any starting model in order to get to this final answer, just the seismic shot gather data. For me, this helped me to realize that fine-tuning training is indeed possible on a CPU. On the right, I'm showing the training loss and the validation loss curves over 50 epochs, and we can see each decreasing over time as the neural network converges to a solution. All right, so conclusions and takeaways. So I was able to successfully train a deep neural network without an accurate starting model to obtain a subsurface model. And the other conclusion I took away is that I was able to train this deep neural network on CPUs with this 4th gen Intel Xeon CPU, which is a big plus for me because GPUs are not always as available. And so to train on the Xeon CPU, when calling the training script, you can use this torch backend Xeon run CPU command and set your device to CPU in your training code. So for example, I wrote out what I would need to do. Instead of just running train.py, I run this line right before it, and I'm saying number of instances is 1, so that's one node I'm training on, and then I'm using 32 cores, so I'm parallelizing across the cores. So a few follow-up items you can have. So one is you can try the code yourself. I have a Medium article with some of the code snippets as well as the OpenFWI implementation. They have tutorials and data sets that you can use to reproduce the results I show here. And then also you can connect with me on the Intel DevHub Discord. So that's a place where developers can come and interact with each other and with folks from Intel. And then the last one that I really want to highlight is the Intel Developer Cloud. So there's a new Intel Developer Cloud where you get access to our latest hardware. And we have just released a server-grade GPU called the Max Series 1100. And it's competitive with the NVIDIA A100. And you can come and try it out there for free. So I encourage you to check that out. And yeah, also visit us at our Intel booth for more demos. So I'm happy to take any questions you might have. In terms of model, do you mean the model architecture was simple, or do you mean in terms of the data set was like? Yeah. So yeah, if we look like you pointed out there, it's very flat line structure geologically. Yeah, and actually the team, the OpenFWI team, has much more complicated looking synthetic data sets as well. I hadn't done the training on those, but they did do some additional training on more realistic geologic looking data sets. And I think based on this, like, you could still extend some of the the same training principles I did here to their data sets as well. Yeah, that's a good question. For this data set, I didn't run traditional FWI on these data, but I know that if you typically if you start with you don't start with a decent starting model. With FWI, you don't end up getting a good final result. Yeah, without that really good starting model, even if you have flatline and the velocities are way off, it'll still won't converge to a proper solution, typically. Yeah.